Okay, how about stroke volume? Can you give me a stroke volume at rest for a normal individual, ballpark? About 60 to 80 milliliters per beat. And an elite endurance athlete, it would be what at rest for stroke volume? Would it be higher or lower? Be higher. They're usually about 80 or 100 milliliters per beat. Let's talk about, let's see, just blood pressure really quick, some normal values for blood pressure. The number on top represents, when we say normal resting blood pressure here is, say, 120 over 80. What are the units on blood pressure? Millimeters of mercury. What's the top number stands for? Systolic blood pressure. Bottom number is diastolic blood pressure. Let's see. Relationships between workload and some of these variables. What's the relationship between VO2 and workload? If you were going to describe VO2 versus workload, the graph, how would the relationship look? Would it be curved? Would it be straight? Would it be linear or nonlinear? Be linear. Okay. Same thing with cardiac output and workload. As workload increases, cardiac output will increase linearly, maybe a little bit of a flattening at the end. Heart rate's the same way. The one that's definitely unique is stroke volume versus workload. As workload increases, stroke volume will increase and then plateau. And that plateau occurs only in normal individuals, and it occurs at approximately what percent of VO2 max does that plateau occur? About 40 to 60% of VO2 max is where that plateau occurs. Okay, now highly trained endurance athletes, do they have the plateau? No, as workload increases, their stroke volume continues to rise. It curves a little bit, okay, but it still continues to increase. Okay, as your workload increases, you're going to increase stroke volume, right, at low workloads. So as I go from rest to moderate levels of exercise, my stroke volume is going to go up. Okay, it could go up one of two ways, theoretically. My end diastolic volume could get bigger, or my end systolic volume could get smaller. If you think stroke volume is equal to end diastolic volume minus end systolic volume, I can either make end diastolic volume bigger or end systolic volume smaller to get stroke volume to be bigger, right? Which one really happens in normal individuals when they go from rest to low and moderate levels of exercise? Which one changes? Does end diastolic volume go up, or does end systolic volume go down? Remember that? Okay, what it looks like is, I don't know if you remember, we had this graph where we had, this is workload, this is end diastolic volume, and this is end systolic volume. So the difference between the two is stroke volume. Remember that? Remember this graph? Looks kind of like. So as you go from rest to low levels of exercise, end diastolic volume goes up, end systolic volume stays basically the same. Okay, so how you increase stroke volume initially is through end diastolic volume going up. Okay, and what's the big player in end diastolic volume going up? What are the two things that influence end diastolic volume? Venous return and preload. So why do you have more venous return and preload as you go from rest to low levels of exercise? This could be like an essay question on the test. Why does end diastolic volume go up? It goes up because as you go from rest to low and moderate levels of exercise, stroke volume goes up because end diastolic volume goes up. Those two go up because venous return and preload go up. What's one of the primary reasons why venous return and preload go up when you start exercising? Okay, as soon as you start exercising, you start doing what with your muscles? Contracting them, and there's a function in the muscle called the muscle pump. Remember the muscle pump veins have valves in them to make sure the blood can only go in one direction. Which direction is that? Towards the heart. So when the muscles contract, if you have a vein going through a muscle, when it contracts, it basically it's like milking a cow. It squeezes the vein and pushes the blood in which direction? towards the heart. That helps increase venous return, increase preload, end diastolic volume goes up, stroke volume goes up. Remember that? Okay. Let's see. Let's talk about cardiac variable changes with exercise with cardiac drift. I'm actually going to pull up the picture of cardiac drift. There was the graph I wanted to show you there. Remember this graph? End diastolic volume going up, end systolic volume staying essentially flat. Okay, here is the graph, not cardiac drift. Okay, remember with cardiac drift, we're talking about what happens with various cardiac variables during a very specific exercise regimen. It is constant workload, submaximal, prolonged exercise. Remember that? Okay, and what we do is we measure the values at the 10-minute mark of exercise, and then we measure them every 10 minutes from there. We look and see how they change from the 10-minute mark. Okay, and the first one to look at is this red line here, which is cardiac output. Okay, over the course of this 50-minute long prolonged exercise bout, what happens to cardiac output? It stays the same. And what's the reason why cardiac output stays the same? What's the reason why cardiac output stays the same? The answer is because workload stays the same. And if workload stays the same, VO2 stays the same. And cardiac output usually follows VO2 and what VO2 does. So cardiac output during this exercise bout is going to stay the same because workload stays the same. The oxygen demand of the muscles stayed the same. It needs a certain amount of blood flow when the heart delivers it. Okay, over time, this green line represents what happens to blood volume. And over time, we have a slight decrease in blood volume. Okay, and there's two reasons why we have this slight decrease in blood volume. Do you remember what they are? One is you sweat, and where does most of the water for your sweat come from? It comes from blood plasma, right? And what's the other reason? Do you remember? It's called hemoconcentration. And it has to do with osmotic pressures within the blood vessels. Once you exercise, osmotic forces tend to pull water out of the blood vessel into what's called the extracellular space. At the end of the day, you lose blood volume. Okay? And then the next one to look at is what happens to stroke volume, which is the black X here. Over time, stroke volume goes down. And what's the reason why stroke volume goes down? What's the reason why stroke volume went down? Because venous return and preload went down. And why did venous return and preload go down? Because blood volume went down. If you have less blood volume, there's less blood to pump back to the heart. Does that make sense? So when there's less venous return and less preload, stroke volume goes down. So what does heart rate have to do in response over time? Heart rate has to go up. And why does heart rate have to go up? Because stroke volume went down and cardiac output stayed the same. So if you want to maintain cardiac output when your stroke volume falls, the only mechanism you have to be able to do it is to increase heart rate. You see that? And that's called cardiac drift. Questions so far? We doing okay?